De Broglie, as we discussed last time, spoke about waves, matter waves, because people thought, anyway, light is wave, so the surprising thing that would be that matters are waves. So a free particle with momentum p can be associated to a wave, to a plane wave, in fact, plane wave with wavelength lambda equals Planck constants over p. So this wave is what eventually becomes a famous wave function. So de Broglie was writing the example, or trying to write the example of what eventually would become wave functions, and the equations for these waves would become the Schrödinger equation. So really, this is a pillar of quantum mechanics. So you're getting there when you talk about this wave. So Schrödinger equation is a wave equation for these matter waves, and this plane wave eventually will become the wave function. And there is a Schrödinger equation for it. Schrödinger equation. So it's a wave of what? He was asked, and Broglie had little idea what that wave was. When you have waves, like electromagnetic waves, you have polarization, you have directional properties. The electric field points in some direction. The wave is polarized. Is there a same property for the wave function? The answer is yes. It will have to wait a little in 804 to see it, but it has to do with spin. When the particles have spin, there are directional properties of the wave, and typically you use several wave functions that correspond to directional components of this wave. So photons are spin 1 particle, electrons are spin 1/2 particles, so there will be directional properties to it. But to begin with, let's consider cases where these directional properties don't matter so much. And for the case of electrons, if the electrons have small velocities, or they are inside small magnetic fields where some of the properties of the spin is important, we can ignore that and work with a wave function that will be a complex number. So it will be a wave function. We'll denote it by the letter psi, capital Psi, that depends on position and time. And that's the wave function. And to begin with, for simplicity, there will be one of them, and it's a complex number. And it's just one wave function. And the obvious questions about this wave function are, is it measurable? And what its meaning is. So is it measurable? And what is its meaning? But to understand some of that, in fact, to realize that these waves are no ordinary waves, we're going to think a little about what it means to have a wave whose wavelength is inversely proportional to the momentum of a particle. That's certainly a strange statement. And probably these are strange waves, as you will see. And by understanding that these are strange waves, we are ready to admit later on that the interpretation could be somewhat surprising as well. And the nature of this number is again a little strange, as you will see. So all that will come by just looking a little more in detail at this formula of de Broglie and asking a very simple question. You have this particle moving with some momentum, and I say, okay, it has this much wavelength. How about a person, if one of you is moving relative to me, like you usually do with Einstein, these observers that are boosted, but let's just do non-relativistic physics, what is called the Galilean transformation, in which there will be another observer moving with constant velocity with respect to you and that other observer compare the results on the momentum and the wavelength and see if you find a reasonable agreement or things make sense. So we're going to try to think of P is h over lambda. And 2 pi's are very useful sometimes. So you put an h over 2 pi here and a 2 pi over lambda. And you rewrite this in terms of quantities that are a little more common. One is h bar, and the other is called the wave number, k. So these are these two constants. And this quantity is called the wave number. The 2 pi's are all over the place. If you have a wave with some frequency nu, there's also a frequency omega, which is 2 pi nu. So we're going to look at this wave, and it has some momentum and some wave number, therefore it has some wavelength. And let's see if we compare things between two different frames, what do we find? So we'll put a frame S and a frame S prime moving with some velocity, moving with velocity plus v in the x direction. So the setup is relatively common. We'll have one frame here, that's the S frame, and that's the x-axis of the S frame. And the S prime frame coincided with the S frame at time equals 0, and now it's moving, so it's now over here. It's S prime. It has moved a distance vt. It's moving with velocity v, and there's t. And S prime has an axis x prime. On this, we're going to write a few things. We're going to say we have a particle of mass m. It has velocity v under bar. Otherwise, I'm going to get all my velocities confused. So this velocity v is the velocity of the frame. V under bar is the velocity of the particle. And v under bar prime, because the velocity depends on the frame of reference. Similarly, it will have a momentum. And all the things we're doing are non-relativistic. So momentum p or p prime. Here is the particle. And that's the position x prime of the particle. And that's the position x of the particle. So that's our system. This particle is moving with some velocity over here, and we're going to compare these observations. So it's simple to write equations to relate the coordinates. So x prime, for example, is the value of the coordinate x of the particle minus the separation. So x minus vt. And I should say it here. We're assuming that t prime is equal to t, which is good non-relativistically. That's fairly accurate. But that's the exact Galilean answer. When you talk about Galilean transformations, and Galilean physics is very useful. Even in condensed matter physics, people write these days lots of papers about Galilean physics. When you have particles moving with low velocities, it's accurate enough. So might as well consider it. And these are the two ways you transform coordinates and time. So from this, we can take a time derivative talking about the particle. So we have dx prime dt prime, or t is your choice. I guess I should put dt prime here, dx dt minus v, which means that the velocity v prime under bar is equal to v under bar minus little v. And that's what you expect. The difference of velocities is given by subtraction of the velocity that the frame is moving. So if this particle has some high velocity with respect to the lap frame, with respect to this frame, it will have a smaller velocity. So the sign seems right. And therefore, multiplying by m, you get that p prime is equal to p minus mv. So if you have that, we would have that lambda prime, the de Broglie wavelength measured by the running person, is equal to h over p prime is equal to h over p minus mv. And it's quite different, quite substantially different from h over p, which is equal to the de Broglie wavelength seen in the lab. So these two de Broglie wavelengths will differ very substantially. Now, if this would be a familiar type of wave, like a sound wave that propagates in a medium, any kind of wave that propagates in a medium, like a water wave or any wave of that type, this would simply not happen. In the case of those waves, you get a Doppler shift, omega is changed, but the wavelength really doesn't change. The wavelength is almost like something you do look at when you take a picture, and whether you take a picture of the wave as you run or you take a picture of the wave as you are sitting still, you'll measure the same wavelength. Let me convince you of that. It's an opportunity to just do a little more formally transformations, because these are going to be Galilean transformations, simple transformations. So our first observation is that the de Broglie wavelengths don't agree. Wavelengths don't agree, which pretty much, I think, intuitively is saying that if you could just sort of see those waves and measure the distance between peaks, they should agree, but they don't, so there's something very strange happening here.